So we should be ready to talk through the results section of this work quite soon. But before I do that, I want to do a quick recap of basically the main idea of what's going on. So on the left here, we have a diagram of a two-level system, and it's interacting with what we call the full environment. So the full environment is given by these green circles here, and these each represent a quantum harmonic oscillator, so a boson. And one thing that we want to ask is, okay, well, what is the heat transfer between this system and this bath? So essentially what we do there is we take the bath, which I'm going to highlight in sort of this pink colour here. So all of this stuff, we say, okay, what happens if we measure the energy of these modes collectively at two different times? So that's essentially doing the two-point measurement protocol, where the projective measurements are made onto the bath Hamiltonian, the full bath Hamiltonian. And again, I'll just mention quickly that I'm going to use the terms bath and environment interchangeably. Right, so people might be thinking, well, how are you planning on doing a projective measurement onto a bath like this? And the answer to that is we don't actually need to do it in like a lab. It's essentially just a mathematical trick that we're going to use. So if we scroll back up to, for example, equation 2, we can see that the characteristic function, which is the quantity that we're trying to calculate, and it contains all the statistics that we're interested in, can basically just be written as the trace of this density operator, which is generalized by this counting parameter chi. So by tracking the reduced part of this generalized density operator, we get access to this characteristic function. So we don't actually need to perform these projective measurements. We essentially we look at how the density operator evolves in time, but we're looking at it in a new way. We're looking at it in this counting field dependent frame, and doing that lets us extract information about heat transfer. Okay, so this is one of our definitions of heat, and this is what we'll probably call the full bath definition. It's changes in the energy of the full bath. And then alternatively, if we perform the reaction coordinate mapping, then we have this extended system, which is made up of the two-level system and the reaction coordinate, and these two can be strongly coupled. And then they are in turn interacting with the residual environment, which let's colour it in yellow. So the residual environment is in yellow here and interacts weakly with the extended system. And if we look closely at this diagram, we can actually see that it only interacts with the reaction coordinate. So the residual environment doesn't actually interact with the two-level system except through the reaction coordinate. So if we look at the system here, we can see that the only interaction that it has is with the reaction coordinate. So from this we get an idea of what we call the residual bath definition of heat. And that's just going to be, okay, what about if we perform these projective measurements onto this Hamiltonian instead? So those are going to be our two definitions of heat that we're going to test. But then on top of defining heat in these two different ways, in the results section, we also make arguments about ergotropy, which is how much work can you unitarily extract from a quantum state. Now, why do we do this? Well, the reaction coordinate mapping we've just seen gives us two definitions of bath, and therefore it gives us two definitions of system, where system loosely is going to mean what we might have control over, and bath is loosely going to mean what we don't have control over. So before we perform the mapping, the system is of course just the two-level system. So we can ask, okay, how much work could I possibly extract from this system? And that's the ergotropy. But alternatively, after we perform the mapping, we could say, well, hypothetically, what if I had access to the reaction coordinate? How much ergotropy could I extract in this case if I had access to the system and the reaction coordinate? Now, the reason that we're doing this is because ergotropy it's essentially how much work you can extract from a quantum state. So our idea is if you can extract work from the reaction coordinate, then it's, let's see, so if you can extract work from the reaction coordinate, and what you have to remember is that the reaction coordinate is a part of the full bath. So we define the reaction coordinate to be essentially a little bit of all of the modes from the full bath. So the reaction coordinate lives inside the full bath like this. So there's a little bit of it everywhere in all of these modes essentially. So if we can show that there's work that could be extracted from the reaction coordinate, then that would mean that the definition of heat which involves the reaction coordinate, which is the full bath definition, probably isn't going to make much sense, because we would expect heat and work to be sort of mutually exclusive things, right? Let's see, how would we say this? Well, let's think. Defining heat is quite a difficult thing to do, but one way that you could define heat is it's not work. So it's a change in internal energy, which is not work. And we can see that by just looking at, for example, the first law. We would say a change in internal energy is made up of a work component and a heat component. So one way that we could define heat is we could just say, well, it's any change in internal energy which is not work. So if it turns out that we can extract work from the reaction coordinate, which we can, then we're going to make the argument that the full bath definition of heat maybe isn't as appropriate as the residual bath definition of heat. So I think there's one more thing to clarify before we start looking at these results, which is the different methods that we're using to calculate these statistics. So the characteristic function is essentially the trace of a density operator, but that density operator is transformed into this counting field dependent frame where the counting field or the counting parameter is chi. And essentially, therefore, calculating these characteristic functions just comes down to tracking this state as accurately as we can. And there's a few ways that we can do that depending on the definition of heat that we use. So for example, if we use the full bath definition of heat, we have two different ways that we can track these statistics. One of them is we can say, well, if we just focus on the independent boson model, which is exactly solvable, it has analytic solutions, it turns out that we can extend those analytic solutions to also calculate this characteristic function, but only if the characteristic function is giving us statistics about changes in the full environment. And if we use these exact dynamics of the independent boson model, then we label our results like this. So this is the characteristic function which encodes statistics about changes in the full bath Hamiltonian using the exact dynamics of the independent boson model. So alternatively, we can use our heat counting reaction coordinate master equation to calculate those same statistics, but using our approximate master equation. Now the reason that we do this is because our approximate master equation is more general than these exact dynamics, because these exact dynamics only work for the independent boson model, and they also only work for the full bath definition of heat. So if we can compare these two and we can show that they're approximately equal to each other, then that's nice because it shows that our master equation is tracking the statistics of the full bath accurately. Now, if that works, which it turns out it does, then we can confidently apply our reaction coordinate method to calculate the statistics of the residual bath, which is what we're going to do afterwards. Okay, and one thing which is quite difficult to try and mention in the paper, but hopefully I'll do now, is there is no way to calculate, as far as we know, there is no way to calculate the heat statistics of the residual bath definition of heat in an exact manner. And the reason is essentially because calculating these characteristic functions comes down to tracking the state of the extended system. And there's, as far as I know, there's no way to do that exactly. There's no analytic solution to the reaction coordinate master equation. Now, if you want a bit more detail, the reason is basically because the the extended system Hamiltonian does not commute with the interaction between the extended system and the residual bath. So this does not equal 0. So therefore you don't get an analytic solution. Whereas if you have the independent boson model, then the system Hamiltonian does commute with the interaction between the system and the bath. Whoops. And therefore, because this commutes, you can get exact dynamics of the two-level system. Okay, let's get started looking at these results then. So first of all, we'll compare the characteristic functions. I actually think I'll just go straight to the figure. So the characteristic function is complex. So we're going to look at its real and its imaginary parts. It's also, the real part is symmetrical and the imaginary part is anti-symmetrical. So essentially we have the phi of chi and t is equal to the complex conjugate of phi with minus chi and t. Okay, so what's going on here? Well, let's have a look at the three different characteristic functions which we're plotting and show or describe the differences between the two. So in green solid, we have the characteristic function for changes in the full bath Hamiltonian, which is calculated using the exact dynamics of the independent boson model. And then we compare this to the characteristic function for the full bath Hamiltonian, which is calculated by solving the heat counting reaction coordinate master equation, which is sort of the main result or the main output of the work that we did. And what do we see? Well, basically we see that there's nice overlap between the two, in the real part and in the imaginary part. Let's ignore the insets for now, I'll come on to that in a second. Right, so green and orange overlap, that's a good thing. It means that the heat counting reaction coordinate master equation is tracking the statistics of the full bath Hamiltonian accurately, which is nice. So then in the purple dotted lines, we have the characteristic function for changes in the residual bath Hamiltonian, and that is also calculated using our heat counting reaction coordinate master equation. And essentially what we're showing here is, okay, look, if we now compare the orange and the purple, these are our two different definitions of heat, and they're calculated in the same manner. They're calculated using this heat counting master equation. So the idea is here that because we're calculating these two characteristic functions in the same way, they're both being calculated using the heat counting reaction coordinate master equation. Any differences between them should be due to the definitions that they are built upon, rather than them being calculated through different methods. Okay, but this is a characteristic function. It's pretty hard to tell what any of this means. Essentially, we kind of need to Fourier transform it, or do something else, which we'll show in the next section, which will give us some physical intuition about what these differences might mean. But before we do that, let's have a look at these insets. Now, the main plots show quite a small range of these chi parameters, and then in the insets we go out to much larger values of chi. And what's interesting is we see some discrepancies between the orange and green curves, which, if we remember, we look at the main plots over a small range of chi, they overlap quite nicely. But as you increase chi, they start to deviate away from each other. And specifically what's happening is the exact full bath definition of heat characteristic function starts to decay down. So it repeats this main feature at chi 0, but you can see that the height of the peak is reduced for the green curve. Whereas for our orange and purple curves, which are based on our approximate master equation, you can see that there's no decay. And we think that this is due to approximations which are made during the derivation of the master equation. So ideally, one thing which would be nice to do would be to take out any approximations that we made to higher order in the interaction Hamiltonian between the extended system and the residual bath. That would then make the master equation itself more accurate, and hopefully would basically bring these peaks down, or at least bring the orange one down, because the orange line should match up with the green line in an ideal situation. But because we've had to make certain approximations, we're not seeing this decay here. And we see similar behavior in the imaginary part here. Okay, so we've just had a quick look at the characteristic function, and we've said the two main conclusions are, for the full bath definition of heat, our approximate method is fairly good at reproducing the exact method, at least in the regime of small values of chi. Right, in the insets we showed that for larger values of chi, the results deviate away from each other. But for small values of chi, around chi is equal to 0, the overlap looks very good. And then we also said, well, there's clear differences between the full bath and the residual bath characteristic functions when they're both calculated using the reaction coordinate method. All right, so the purple and the orange lines don't look the same. But then the question is, well, what do those differences mean physically? Because this is a characteristic function, it's the Fourier transform of the probability distribution. So it's hard to see immediately what these differences are going to mean. And then we can come on to a really nice result, which is, well, not result, but just a way of calculating something. So the characteristic function is, again, the Fourier transform of the probability distribution. But we can easily extract moments from that probability distribution by taking derivatives of the characteristic function and evaluating them at chi is equal to 0. Now, why is that a nice thing? Well, because our method works really well at chi is equal to 0. So it might not be very good at getting the full probability distribution, because that would involve calculating the characteristic function out to really large values of chi and then taking the inverse Fourier transform. And we can see that at large values of chi, our method appears to be breaking down due to certain assumptions that we have to make during the derivation of the master equation, which the results are based on. But if it works well close to chi 0, then we should be able to extract low order moments, so the mean and the variance basically, from an equation such as this. So the question is, how are we now going to take derivatives of our characteristic function and evaluate them at chi is 0? And the answer is we just use a finite difference approximation. So that's what we then do in figure 3. And before we do that, let's just pause and mention the fact that we're actually able to calculate the mean and the variance for the full bath definition using the exact analytic case. So we end up with these two nice expressions for the mean and the variance of the full bath definition of heat when we use the exact method of calculating the dynamics. And again, we're going to do this two-step process. We're going to check that the exact and our method for calculating the full bath definition agree. And then we're going to compare the full bath and the residual bath definitions. So that's what we do here. So essentially what we do is we say, okay, nice, the green and the orange lines agree with each other. That means that the reaction coordinate method is working well. And then we say, let's look at the differences between the orange and the purple lines. Those are the differences in our definitions of heat. So let's do that now. So first of all, let's just explain what's happened in this plot. So in the top row, we have the mean, and in the bottom row, we have the variance, and things are scaled appropriately by energies, so that things are dimensionless. And let's see, so the left-hand plot shows a very small region of time, and then the right-hand plot shows a long region of time. This was quite an awkward plot to try and make, but hopefully that makes sense. So here you can see we're going out to 250, whereas in this right-hand plot, we go from 0 all the way up to 25,000. So this left-hand plot here is essentially just the first little part of this right-hand plot, just zoomed in so that we can see what's happening. See these oscillations, and we can see that the overlap is quite nice. So let's have a look at what's happening. Let's focus on the mean first. So the full bath definition seems to be oscillating quite heavily before it reaches some steady state value. And I think this is where the full bath definition of heat starts to break down, because, well, do we expect heat transfer to go in two directions, or do we expect it to sort of just monotonically increase to some steady state value? I think it's the latter, and that's what we see with the residual bath definition in purple here. Now, even there are some slight oscillations, and we don't know what that's from. It could, again, just be due to the master equation not being as accurate as it could be, right? Because this isn't necessarily a monotonic increase, because we have these periods of decrease in mean heat here. But on the whole, I think it looks like a more reasonable accumulated heat transfer that you would expect. So maybe at the start there's quite a rapid increase in heat transfer, and then as the two things start to equilibrate, then the amount of heat transfer levels off like this. And we see a similar story when we look at the variance. It's pretty much exactly the same plot, except things are scaled differently. So the next thing that we move on to is calculating the ergotropy and the von Neumann entropy of our two definitions of system. So what we care about is, okay, well, how much work can I extract from the system, and how does its von Neumann entropy change with time? And then we're going to compare that to the extended system. So we're going to include the reaction coordinate in that analysis as well. So here we just show how to actually calculate the ergotropy, and then in figure 4 we plot the ergotropy on the left-hand plot. So let's have a look first at the two-level system ergotropy. So that is how much work can I extract from this system here. And what's happening? Well, the ergotropy decays down quite quickly, and then it appears to increase. Well, it does increase, right? And then this happens periodically, and the amount that the ergotropy reaches at its subsequent maxima decreases in what looks like an exponential fashion. Now, what's interesting is that these oscillations line up perfectly with the oscillations of the mean heat of the full bath. And they also line up, if we scroll down to the appendix, with the oscillations in the two-level system coherence. So what's happening here is our system is interacting with this bath, and this bath is non-Markovian. So it's exchanging energy and information in a reversible way with our system. And that's what we're seeing in this plot here. So the system loses its coherence for a time, and then it gets it back from the bath. And then it loses it again, and it gets it back again. And that's exactly what's happening with the ergotropy too. Because one interesting result is that you can use coherence as fuel for ergotropy. So in this region of time here, the system has gained coherence back from the bath, and it can use that as ergotropy, like such. And during this time is when there are these changes in heat of the full bath as well. So essentially, the argument that we try and make here is, well, there's a bunch of reversible exchange of energy and information between the two-level system and the full bath. And therefore, that doesn't really sound like heat transfer, does it? Heat transfer we expect to be in one direction, from hot to cold. And therefore, we use this as an argument to back up the idea that the full bath definition of heat is perhaps not appropriate in this regime. And then further evidence is added to this if we look at the ergotropy of the extended system. So what's happening here? Well, you can see immediately the ergotropy of the extended system is much higher than that of the system at all times. And what does that mean? Well, essentially it means that the coherences are getting exchanged between the system and the reaction coordinate. And as long as they maintain inside the extended system, then they can be used as fuel for ergotropy, which is why the ergotropy of the extended system remains high. So if we remember that the reaction coordinate essentially lives inside of the full bath, it's sort of distributed around the full bath, the exact same thing is happening. So coherences are going from the system to the reaction coordinate, and then we can think about them perhaps being passed around by the full bath, and then they eventually go back to the system. So that is what's happening if we look back at this diagram here. The system passes its coherences to the bath passes it around modes in the bath, and then they eventually give it back to the system. and then we get this recoherence here. And then that's why we see these same oscillations in the ergotropy of the two-level system as well. So this result essentially tells us, excuse me, that if you have access to the reaction coordinate, then you can extract more work than if you only have access to the two-level system. So what does that mean? It means that energy changes of the reaction coordinate are related to work transfer or an exchange of work, and therefore they shouldn't be defined as heat transfer. Now, why is that interesting? Well, because as we said, the reaction coordinate kind of lives within the full bath. So if we can't define changes in the reaction coordinate as heat, then we shouldn't be able to define changes in the full bath as heat either, because the reaction coordinate lives inside the full bath. And again, this argument is further backed up, maybe not in the most satisfying way compared to the ergotropy, because comparing von Neumann entropy with thermodynamic entropy is well, it's not as straightforward as it might sound. So we look at the von Neumann entropy of our two-level system and our extended system states, and what do we see? Well, we see that the two-level system entropy doesn't increase monotonically. It has these small regions where it decreases. And again, if we try and make the analogy with thermodynamic entropy, you would think that if something is in contact with a heat bath, you would expect its entropy to change monotonically. So for example, if you have, what's a nice example? So if you have a cup of coffee in a room, then you expect the coffee to decrease in its temperature and equilibrate with the room, and the entropy of the coffee you would expect to change in one particular direction. So if it's going from hot to colder, then it's going to decrease its entropy as that happens. Now this is the opposite argument, right? The two-level system starts off by increasing its entropy. So what would that be? That would be, for example, an ice cube melting in a room. We go from low entropy to high entropy. So what's happening here is, I mean, this might not be the perfect analogy, but imagine that our ice cube is melting and then it starts to freeze a little bit again. Now that isn't a perfect analogy, but I think it highlights the point in some way. So if you had a situation like that, if you had an ice cube which melted and then refroze slightly, you wouldn't say that this is definitely in contact with a heat bath. Right, you would say, okay, maybe you put it back in the fridge and some work transfer occurred. At the freezer, not the fridge. So again, we think that this backs up the argument that the two-level system is not in contact with a heat bath, and therefore we cannot define changes in the full bath Hamiltonian as heat transfer. So I guess now we'll just quickly read through the discussion. So we've said we've used the two-point measurement protocol to calculate the full statistics of energetic changes in the independent boson model in the non-Markovian regime. We employed the reaction coordinate formalism, which accounts for the two-level system environment correlations through the reaction coordinate, which enables us to study the energetic changes in the environment in the strong coupling and non-Markovian regimes. It also allows us to investigate how different system environment partitions impact the definition of heat in open systems, right? So that's our full bath versus our residual bath definition of heat. And then the first bit is basically just saying that the reaction coordinate master equation lets you look in the strong coupling and non-Markovian regimes. Okay, so we find that a naive definition of heat, which is the full bath definition, overlooks work-like contributions in the interaction, right? So these big oscillations that we're talking about. Okay, so we can also consider the residual environment as a definition of heat. We see that these coherent oscillations in the mean and the variance get suppressed. And this suggests that heat transfer between the extended system and the residual environment is irreversible, which is what you expect of heat transfer. And then this is supported by the ergotropy and von Neumann entropy arguments that we make. Okay, so this paper came out while we were writing up, which essentially kind of shows the same thing. So they show that if you've got a heat bath with a sharply peaked spectral density, it acts like a work reservoir, which is what we're showing here. So I guess we should have mentioned really that we are interested in situations in this work where the spectral density of the full bath is sharply peaked. And essentially this work by Koller and Brewer shows that this acts like a work reservoir, even if the bath begins in a thermal state. So essentially the long and short of this work is, if you want to define heat for an open quantum system, you need to be careful. You need to think about the shape of the spectral density, the coupling to the bath, and then perhaps if you have a non-Markovian environment, you should use the residual bath definition of heat like we have here. So in the appendix, we have some benchmarking dynamics where we essentially just show that the reaction coordinate master equation can track the dynamics of the system very well. That's what we show in this figure here. And let's see, so on this long time scale, we see these recoherences of the system. This essentially just shows us that we're working in the non-Markovian regime, because a Markovian master equation would not be able to predict this. And then in the second part of the appendix, we show what the heat counting reaction coordinate master equation looks like. And it has this nice form. Let's see, so we've got a coherent part of the dynamics, and then we just have these different rate operators acting on our extended system generalized density operator. We show what these rate operators look like, and then we also have these generalized forms of the bath correlation functions, and then we get definitions of the rate operators, and they all depend on the difference in eigenenergies of the extended system Hamiltonian. And what's really nice about the heat counting reaction coordinate master equation is it depends on this parameter chi, and if you just set chi equal to 0, we get the reaction coordinate master equation back. Okay, that's going to be it from me. Hopefully, if anyone reads this paper and they find this video, it's been useful. So if anyone's got any questions that they want to ask, my email is here. It's also listed on the paper. I should also mention that anything that I've said in this video which might have been wrong is my fault, and no blame should go to my two supervisors and co-authors, Jake and Essen. So thanks for watching, and if anyone's got any questions, feel free to reach out to me. I'll do my best to answer them.